Hi everybody, I'm Jakob Hoydis from NVIDIA, and I'm going to present today some joint work with two of my former colleagues from Nokia Bell Labs in Paris, Mathieu Goutet and Faisal Aitaoudia, as well as Jean-Marie Gors from INSA Lyon. During the last years, we have worked quite extensively on the idea of end-to-end learning for the physical layer, where parts of a transmitter and a receiver are jointly optimized for a particular channel or channel model. But so far, we have always taken the underlying waveform for granted. And we now wanted to push the boundaries of end-to-end learning even further to see if we could include the waveform design as well. Here are the references to two papers on the topic that we have put on archives this week. And my talk today will be based on material from this first paper. But I also encourage you to have a look at the second, which looks at waveform learning for single carrier systems. But before delving into technical details, and because this is a 6G workshop, let me start with a very simple 6G vision that fits on one slide. Thanks to Moore's law, we have seen increasing processor performance and efficiency over the last decades. However, Moore's law has essentially come to an end by now, and domain-specific accelerators are one way to continue scaling performance and efficiency. Wireless communication systems are traditionally designed to work robustly in a wide variety of scenarios. And a bit like a general purpose processor, they can be seen as general purpose wireless bit pipes. Therefore, we believe that 6G systems should be able to specialize to the radio environment in which they are deployed and to the application they serve. And since this specialization must be automated, it can only be achieved through software-defined radio access networks and machinery. Now, looking at 5G, OFDM has, of course, many practical advantages, but also at least two quite well-known shortcomings. First, the peak-to-average power ratio is high, which leads to power amplifier inefficiencies. And second, the spectral confinement or adjacent channel leakage ratio is not great, so that guard bands are required, which reduces the spectral efficiency. The definition of PAPR on this slide might be slightly different from what you are used to. So here it's defined as the minimum threshold E, for which the probability that the ratio of the instantaneous squared signal amplitude and the average power is larger than E is smaller than epsilon. So in other words, you want that high signal peaks have low probability, but you do not care about the maximum, which happens very rare. And in this work, we were wondering if one could learn to transmit a signal on top of OFDM while controlling finely the PAPR and ACLR. Now, we frame this as a learning problem in the following way. So we consider an autoencoder where the transmitter is a neural network with parameters theta that transforms a bunch of bits B into a complex valued vector X, which is then modulated via OFDM. Then we have a channel and an OFDM demodulator, which generates the vector Y. And this is then fed into another neural network that produces log likelihood ratios for all of the bits. And so this neural receiver network has parameters psi. Now, assume that we have n subcarriers and transmit k bits per subcarrier on average. The quantity that we want to maximize is an achievable rate, so C of theta and psi, that consists of two terms. The first term is the sum of the bitwise mutual information or the bit metric decoding rate, assuming an ideal receiver. So this is independent of what happens after Y. Second term is actually a rate loss due to a mismatch receiver, which outputs slightly erroneous a posteriori bit probabilities or LLRs. Now, maximizing this rate under PAPR and ACLR constraints is a constraint optimization problem, in which we want to achieve that the average energy per OFDM symbol equals n, We want that the PAR equals a target value gamma peak, and we want that the ACLR is smaller or equal to a target value beta leak that we fix. We train our system using stochastic gradient descent, and which requires, of course, a differentiable loss function. And for this reason, we express the objective and constraints as differable functions that we can evaluate during training. And we use the augmented Lagrangian method to convert the constraint problem into a single loss function. So let's go through this step by step. Maximizing the achievable rate that I've shown in the previous slide boils down to minimizing the sum of the binary cross entropies, where the expectation here is simply approximated using Monte Carlo sampling with a batch of B as samples. Our first constraint, so this average energy constraint, can be enforced by using a normalization layer that normalizes the variance of each batch. So it's a bit like batch norm. Now, concerning the second constraint, the PAPR, here we want to penalize all time instances in which the squared signal amplitude is above the threshold gamma peak. But since we cannot compute the integral over t, because we also do not know exactly the waveform s of t, we approximate it by a Riemann sum on the oversampled signal. So z underscore ti, this is actually the discrete oversampled version of s of t, which can be done by a simple IFFT FFT operation. So where you insert zeros in the spectrum, which is fully differentiable. And lastly, the ACLR inequality constraint is first converted to an equality constraint with a slack variable. And we can then approximate the ACLR using the ratio of two quadratic forms, in which the matrices W and V are pre-computed and do not depend on X. So they only depend on the fact that we use OFDM. Now, with all of these ingredients in place, we have our single augmented Lagrangian loss function, which is iteratively minimized according to algorithm 1. And you have 5 hyperparameters on top of the neural network weights, namely lambda p, lambda l, mu p, and mu l. And there's also a tau somewhere hidden in the algorithm that need to be initialized. And once you've done this, you have a loop in which you carry out a few steps of stochastic gradient descent, followed by an explicit hyperparameter update. And so this gives you then a new loss function, which you minimize again using SGD and so on. And you do this until your algorithm is essentially converged, or you don't see any performance improvements anymore. Now, in order to have a very competitive baseline, we have implemented a tone reduction scheme where several subcarriers are sacrificed to transmit so-called peak reduction signals, C of n. So the goal is to find this peak reduction signal vector C that minimizes the maximum signal amplitude within an OFDM symbol. And so this can be, again, approximated by oversampling the discrete OFDM symbols, which you can simply do by using a larger IDFT matrix. And the resulting optimization problem is then simply convex and can be efficiently solved, for example, using a solver such as CDXPy. Also note that we use a different randomly chosen set of subcarriers for peak reduction in every OFDM symbol, which was shown in the literature to achieve the best results. So this is, of course, not something that you can implement in practice, but we wanted to have the strongest baseline possible. Let us now have a look at some simulation results. So these were all generated for an AWGN channel and an OFDM system with 75 subcarriers. So the odd number here was chosen simply for symmetry reasons. The tone reservation scheme was implemented using different numbers of PRTs, so to trade off spectral efficiency against reduced PAPR. And the end-to-end system was trained for 2 different ACLR targets, -20 and -30 dB, as well as different PAPR targets in the range from 4 to 9 dB. So let me walk you through the figures. So in the top left plot, you can see the achievable rate versus PAPR for the various schemes. And the takeaway message from this is that we always outperform the baseline significantly. But let's focus on one specific point. So I hope you can see my mouse pointer. So at an ACLR of minus 20.9 dB, we get a PAPR of 6 dB and a rate of 3.1 bits per second per hertz. The baseline at this point, so this green curve, has roughly 10% lower throughput. You can also do the comparison in the horizontal direction. So for example, the baseline system there has the same rate and the same ACLR, but 1.5 dB higher PAPR. Now in the center plot, you see the CCDF of the squared signal amplitude for the baseline in our scheme. So at this last operating point, so where our scheme has simply 1.5 dB less PAPR. And you can see that our training directly impacts the CDF of essentially the envelope of our signal. Okay, and on the top right plot, this is just to visualize the power spectral density of the various schemes so that you have an idea of how different ACLR values impact the spectral behavior. Let me now conclude. So in summary, we have shown that PAPR and ACLR constraints can be efficiently included in the end-to-end learning process. And this was done by using time domain oversampling and Riemann sums to compute the PAPR. We used a simple quadratic form with pre-computed matrices that allows us to measure the ACLR. And last, we have the augmented Lagrangian method for iterative stochastic gradient descent-based training. And I think that these three ingredients kind of opened the door to the whole field of waveform learning. And I'm excited about the possibilities that this offers for various applications. Now, looking forward, I believe that this was essentially the last missing piece to learn entirely new physical layer schemes. So we can now learn new codes that achieve state-of-the-art performance. So I think this whole idea of turbo autoencoders is very exciting. We can learn new modulation schemes and bit labelings together with a receiver that allows us to get rid of pilot tones. And we can now also learn new waveforms. And the cool thing is that these techniques can now all be combined together to learn bespoke communication schemes for specific environments, hardware applications, maybe even for joint communication and sensing. And yeah, I hope that this might be one of the enabling technologies for 6G, and I look forward to your questions. Bye-bye.